explain one study about the effect of tree canopy cover on mortality, so air pollution related to mortality. So this is a study performed in Europe. So, but you can extrapolate in Asia and in Thailand if you want. So just a few words about the adverse air pollution effects. So you know you have adverse impacts on the human health, in particular on respiratory and cardiovascular disease. You have also impacts on materials, on buildings, for instance, on biodiversity. So we observe a strong and significant decline of biodiversity in cities in particular, and on ecosystems, forest ecosystems. So you have impacts on plant health and on trees. So you can observe defoliation and discoloration of leaves or needles. And for instance, you have specific ozone symptoms, injuries on the leaves. So red or brown dots, and chlorotic motors is a yellow path on the leaves surface or needles. This is specific to ozone. So air pollution impacts. So leading to almost 4 million of premature deaths in 2019 at a global scale. It's a major public health issues. In cities, so citizens are exposed to more than 200 classes of air pollutants or air pollutants. As I previously explained, so we have 3 different and major air pollutants in cities: ground level ozone, fine particles, and NO2 for human health, ecosystems, and biodiversity. So billions of people are exposed to levels of PM2.5 or 3 NO2 above the World Health Organization air quality guidelines for human health protection. By 2050, almost 70% of the world population will live in cities, leading to almost 7 million of premature deaths. So, previously explained urban greening, you have some co-benefits for air quality with a reduction of air pollution, climate with a reduction of local air temperature, and a mitigation of urban Thailand, and citizen well-being. So in this study, we estimate the changes over time in tree canopy cover over the past 20 years in 744 urban centers, so urban areas, with more than 50,000 inhabitants across 36 countries in Europe. For that, we conduct a quantitative health impact assessment to estimate the effect of tree canopy on air pollution and on the related mortality in each city and each year. So if you have questions, maybe in case if it's not clear, you can ask me. So first step, we define urban center and population. So all the study was performed at 1 kilometer of spatial resolution. It was not easy and not needed to have a better spatial resolution. So here you can see the different delineation for all urban all cities, urban areas with more than 50,000 inhabitants. So first step is to categorize each grid cell as urban center or not. So for that, we use a global human statement layer. So with the definition of urban center by density, with more than 1,500 people per grid cell, continuity of grid cell, and total population exceeding 50,000 inhabitants. So for that, we use the World Pop dataset. So it's at a global scale, right? So this is for the definition of urban center and to get population data. Second step is to get air quality data set at the same spatial resolution. So we have a data set at global scale published by Susan Annenberg from the US. So you are able to get such data from 2000 until 2019 for all cities in the world. So the air quality data set is combining satellite observation from different satellite missions like MIS and MRIX. Chemical transport model like Chimère, WRF, Geochemistry, and ground-based observation. So by combining all these data sets, she provides a very good air quality data set with annual data. First step is the quantification of tree canopy cover. So for that, we use the data at 30 meters of spatial resolution. Landsat, I explained previously, we can use Landsat tree canopy 8-inch dataset. It's a dataset provided by the University of Maryland in the US from gathering all yearly estimates of tree canopy with a very good accuracy. And this dataset is available at a global scale, so even for Bangkok, you have. So in city, where you have non-native and ornamental or exotic tree species, so we adjust the tree height from 5 to 3 meters of height. Because in the Landsat tree canopy 8-inch dataset, the first dataset is providing the tree height from 5 meters. But you can adjust and you can extract the data for all trees over 3 meters tall. So estimates are provided with spatial resolution of 30 meters. And for each urban center, so you have the delineation, and for each urban center, we sum and calculate the average tree canopy from all 30 meters pixel estimate. Now, more complicated is the pollution-related premature mortalities at 1 kilometer of spatial resolution. So for that, we apply the health impact function. So established by the World Health Organization. So using the relative risk. First step is to calculate the population attributable fraction for each grid cell. So for that, we need relative risk. So relative risk is the probability of increase of one disease for each 10, for example, 10 ppb of increase of pollutant. So using meta-analysis published by the World Health Organization, you can find not city-specific, but regional specific relative risk for main air pollutants, in our case ozone, PM2.5, NO2, for mortality. So you have all causes mortality. You have causes for respiratory disease, cardiovascular disease. You have different disease, and you can select the disease related to air pollution. In our case, we use all causes mortality, non-accidental causes. We exclude non-accidental causes. So in this case, you need relative risk, so it's published. Sometimes from epidemiological studies, you can find such relative risk values at the city scale for the main cities, but also at the national scale. For comparison between regions, we used European relative risk. And using the population data extracted from World Portal. Second step is to calculate the mortality due to air pollution for each grid cell. So it's easy. So the mortality burden is calculated from the baseline mortality. So for each city, you know it's published by the epidemiological institute. The baseline mortality is I don't know if it is average mortality in each city for each urban center and population. So you need just to multiply the population attributed fraction with the population and the baseline mortality. Baseline mortality, for instance, is 1,000 for per 100,000 people. For the trends analysis, because I told you we investigate between 2000 and 2019, so we use the non-parametric in order to skip the data distribution, and also for environmental data, it's much better and robust to use non-parametric test. So we use the maintainer test and slope estimator to detect and estimate the magnitude of trends. So now we have the air quality data, we have the mortality data, we have the population data, we have the tree canopy cover, and we combine all data in order to establish a model to correlate and to estimate the effect of urban tree canopy on air pollution and mortality. So for that, we need the linear mixed effect model. So the linear mixed effect model is able to count the intrinsic difference in air pollution between cities and over time. So we use as a random effect city and here, and the tree cover is a variable of interest. So using this kind of statistical model, we are able to take into account the difference between the cities. For instance, you don't have the same air pollution condition, or you don't have the environmental, you have different environmental conditions, number of vehicles, different population. So all the differences are taken into account over time. So for that, we obtain a very good coefficient correlation. So 85% is explained by the model. And we did all statistical analysis at the citywide scale over the time period 2000-2019. So this is to show you So the trends in PM 2.5 and NO2 in Europe, so worldwide, but in Europe, so you have an improvement of air quality, so in particular in Europe and North America. In India, no. And Bangkok, it's between 0 and 1 plus, yes, an increase of PM 2.5. Slight increase. So in Europe, so we observe an increase, a decline of PM 2.5 by almost 1%, and also for NO2 almost 1.2% per year. For ozone, so in this case we used the summer mean daily 8-hour maximum ozone concentration, because this metric, ozone metric, is significantly correlated with health, with the health data, compared to the ozone mean concentration. So in Europe, we observe one increase of ozone in cities due to lower ozone titration by NO. You have a decline of NOx emission, mainly due to the road traffic. So we have a decline of NOx, but we have an increase of ground level ozone in cities, while we observe a decline of maximum ozone concentration, so in particular in summer. So in our case, in cities, we observe an increase of ozone. So now for the mortality, so we calculate for each air pollutant, in this case NO2, the attributable mortality. So for all countries, we did a box plot using the average, median, max, mean value, extreme value, all data, all together, and we calculate the attributable proportion of death due to NO2. In this case, it's due to fine particles, PM 2.5, for ozone, and total. So in our case, for instance, in France, almost 12% of total deaths are due to air pollution. So the three main air pollutants, ozone, PM 2.5, and NO2. This is median value, almost 12%. So now, tree canopy cover. So in Europe, the urban tree coverage is the mean urban tree cover is almost 19% over the study period 2000-2019. So the highest proportion of tree cover is observed in Finland, with a mean city tree cover of 36%, Switzerland 30%, and Belgium 26%. While we observe the lowest proportion of tree cover in Malta. Malta is a very small island between, in the Mediterranean Sea, between Sicily and Tunisia, Africa and South Europe. So Malta is a sand island, you have nothing. So 2%. Kosovo is in ex-Yugoslavia, close to Albania, and Romania, so in Central Europe, with almost 5%. So we calculate the trends in a tree canopy cover. On average, in Europe, we have a slight increase of tree cover in cities. In 76% of cities, we observe an increase of tree cover. Yes, 76% of cities, you have an increase. On average, 0.22% per year. However, we observe a decline in Scandinavia. In Northern Europe, you have a decline of tree cover. For instance, in Finland, almost 0.6% per year as decline. And we have a strong increase, the highest increase in Romania, with plus 1.9% per year of increase of urban tree canopy cover. So here you have the result of the linear mixed effect model. And so you correlate, this is the output, you correlate the ozone concentration, PM2.5 and NO2, with the tree cover. And you have a very good correlation, significant correlation between the tree cover and the air pollution. The air pollutants concentration, not air pollution. So for each 5% points, or 5% points, I mean is, for instance, if you have a tree cover of 10% in the city, 5% point increase is you pass from 10 to 15. So for each 5% points in tree canopy cover would reduce ozone by almost 1.2%, PM2.5 by 2.8%, and NO2 by 1.4%. For each 5% increase, you have a reduction of air pollutants in urban cities, in urban areas with more than 50,000 inhabitants. So you have the impact on, you have the correlation and the relationships, the function between tree cover and air pollutants concentration. So at the end, you know the impact on air pollution related mortality. Because if you, with this relation, if you increase the tree canopy cover, you know the impact on air pollution, and at the end you are able to calculate and to quantify the impact on mortality just by applying the health function as presented before, using the relative risk. So in our case, in this figure you have the impact by increasing the tree canopy cover from the current condition, so the year 2019, to 30%. For instance, I don't know, in Aix-en-Provence, the tree canopy cover is around 25%. We calculate the impact on mortality by increasing the tree canopy cover from 25 to 30. In Albania, for instance, from 10% to 30%. For each city, we calculate and we estimate the impact on mortality. On average, if in all cities we increase the canopy cover from the current condition to 30%, we will reduce the number of deaths by almost 10 deaths per 100,000 people. With the lowest impact, so less than 10 deaths in Western and Northern Europe, and the highest impacts, more than 20 deaths in Eastern Europe and former Yugoslavia, like in Kosovo, Albania, and Montenegro. So we also calculate an hypothetical scenario. If we cut all trees in cities, what is the impact on air pollution? So using the linear mixed model, you are able to know by cutting all trees with a tree cover of 0, 30%, 20%, etc. So in this case, if you cut all trees in cities, you increase the number of deaths due to air pollution by 8 deaths per 100,000 people. With highest increase in Eastern Europe, Poland and Slovakia, more than 25 deaths, additional deaths. So in this table, I gather all data. So here you have the number of cases, so the number of deaths with the current condition. So last year it was available years was the year 2019. So we calculate the number of deaths due to air pollution in each country, in each city, and at the end in each country, European country. For instance, in France, you have almost 13,000 deaths due to air pollution in 2019. We calculate the benefits, the number of deaths, the reduction of deaths by increasing the tree cover to 30%, and the increase by cutting our trees, so the tree cover of 0%. In total, so in 744 cities, by increasing the tree canopy to 30%, could prevent almost 12,000 deaths each year. So in this case, representing 9% of the total death. By removing all trees in cities, so 25,000 additional deaths each year. So in this case, we plot the number of cases per 1,000 people, and the tree canopy cover, so 0%, 30%, and for each increase, 5% increase. And you observe reduction of death. So compared to 2019, each 5% increase in tree canopy cover, you observe a 3.6% reduction of air pollution-related mortalities annually, almost 5,000 deaths. So the mean tree canopy cover was 19% in Europe. We observe an increase of tree canopy cover within not 76 but 73% of urban centers. We observe an increase of tree canopy cover. Only 25% of the total population in Europe lived in area with a tree canopy cover exceeding 30%. Each 5% increase of tree canopy, so you have a decline of PM 2.5, 2.8%, 1.4% for NO2, and 1.2% for ozone. Each 5% increase in tree canopy cover prevent almost 5,000 deaths due to air pollution. Reaching a tree canopy cover of 30% could prevent about 12,000 deaths annually. So as I explained last time, so reaching a tree canopy cover of 30% is very challenging, in particular in densely populated cities, but also due to the water scarcity. So in arid region, for irrigation, you have a problem. So we are moving from 30% tree canopy to 30% of vegetation cover for urban greening plants. Very important, peri-urban reforestation, greening is very important because you have an impact of the peri-urban forest on air quality in city and also on air temperature. So if you cannot plant in cities, you can plant in the urban, peri-urban and suburban areas in order to improve air quality in cities. Thank you so much.